Imagine holding a diamond, feeling its weight and admiring its brilliance. Its strength and clarity come from a perfect repeating pattern of carbon atoms, meticulously arranged in a lattice. This ordered structure is what gives it its remarkable properties. We know solids with their fixed shapes and volumes, liquids flowing and adapting to their containers, and gases as the basic states of matter, each defined by its unique molecular behavior. But what if there was another phase, a state of matter beyond our everyday experience, stranger than fiction, a material whose structure repeats not just in space like a conventional crystal, but also in time? This is the reality of a newly discovered phase, a concept that was once purely theoretical, the time crystal. A time crystal's parts move in a perpetual repeating rhythm, an intrinsic oscillation that defies equilibrium, seemingly forever, a self-sustaining dance at the quantum level. This occurs without external energy input, a phenomenon that challenges our understanding of physics. This challenges our deepest intuitions about the universe, about how systems behave over time, where things usually wind down and entropy always wins, dictating a natural progression towards disorder. Yet, time crystals exist in constant, ordered motion, a defiance of this universal tendency. A rhythmic pulse locked into a pattern that repeats through time, an eternal metronome at the atomic scale. Their discovery forces us to reconsider the rules of matter and energy, pushing the boundaries of what we thought was possible. These aren't magical artifacts conjured from fantasy, but a genuine, experimentally confirmed phenomenon, observed and replicated in laboratories around the world. Time crystals open a door to physics, revealing a landscape where the familiar rules of thermodynamics are bent in fascinating ways, challenging our fundamental assumptions. Exploring this new state is like being an astronomer in Galileo's time, a moment of profound discovery. What we see is fundamentally new, a glimpse into uncharted territory. The journey into time crystals is a journey into quantum mechanics, a realm of bizarre and counterintuitive phenomena, where the impossible becomes possible, and the very fabric of reality seems to shift. Here, a crystal structure is found not in three dimensions of space as we typically understand it, but in the single forward-marching dimension of time, creating a pattern that repeats eternally. Welcome to the world of time crystals, a frontier of physics that promises to reshape our understanding of the universe. For centuries, inventors dreamed of perpetual motion machines, devices that run forever without energy input. But the laws of thermodynamics say this is impossible. Energy can't be created or destroyed, and entropy always increases. That's why pendulums stop and hot coffee cools. The quest for perpetual motion has always been a dead end in physics. When time crystals were first proposed, they sounded suspiciously like this forbidden dream, a system whose parts move in a repeating cycle forever without energy input. It seemed to break the rules. But time crystals don't violate thermodynamics. They're a new form of non-equilibrium matter. A time crystal doesn't generate usable work. Its perpetual motion is a quantum phenomenon. It exists in its lowest energy state. Its ground state yet still exhibits periodic motion. It's like finding a ball at the bottom of a valley that keeps bouncing forever. This paradox is only possible through the strange rules of quantum mechanics. Time crystals are not perpetual motion machines, there's something even more intriguing. The story of time crystals began with a profound question, a challenge to our fundamental understanding of the universe. It all started from the brilliant mind of Nobel laureate Frank Wilczek in 2012. He dared to ask a question that would reshape the landscape of physics. He wondered, if crystals with their beautifully ordered atomic structures break the symmetry of space, exhibiting a repeating pattern in three dimensions, could something, some exotic state of matter, break the symmetry of time itself? Could there be a structure that repeats not in space, but in time? In a regular crystal, atoms are arranged in a highly ordered fashion, forming a repeating pattern that extends throughout space. Wilczek imagined a quantum mechanical system, a collection of atoms or particles, whose lowest energy state, its most stable configuration, would not be static and motionless, but would instead move in a repeating rhythmic oscillation, a perpetual dance at the quantum level. This would effectively break time's uniformity, its continuous, unbroken flow. He proposed the existence of a time crystal, a revolutionary concept that challenged the very foundations of physics. A time crystal would tick like a clock on its own, exhibiting periodic motion without any external energy input, even when it's in its ground state, its lowest energy state, where all motion should theoretically cease. This was a radical idea, a paradigm shift in how we understand the nature of matter and time. It suggested that motion could be a fundamental property of matter, an intrinsic characteristic even at its most stable and quiescent state. The concept was undeniably elegant, beautifully simple in its conception, but also deeply controversial, seemingly flirting with the forbidden idea of perpetual motion, a concept long considered impossible by the laws of thermodynamics. Wilczek's groundbreaking paper ignited a firestorm of debate within the physics community. Many physicists vehemently argued that such a system, a self-perpetuating motion machine, simply couldn't exist in a state of thermodynamic equilibrium, where energy is minimized and the system is at rest. Initial theoretical work, based on established principles of physics, seemed to confirm this skepticism, suggesting that a time crystal, as originally conceived, was indeed impossible to create in a closed system at equilibrium. But the sheer audacity of the idea, the tantalizing possibility, inspired other physicists to look for loopholes to explore alternative scenarios. The focus of the investigation shifted. The question was reframed. Could time crystals perhaps exist in systems that are continuously driven, kept out of equilibrium by an external energy source? And so, the search for time crystals had officially begun, a quest to find these elusive entities, not as a mere fantasy or a theoretical curiosity, but as a serious scientific endeavor, a challenge to the established boundaries of physics and our understanding of the universe. The dream of time crystals was alive and well, and the hunt to find them was officially on. Time crystals quickly evolved from a theoretical concept to a tangible quest, a search to uncover new and exotic forms of order in the enigmatic quantum world. The journey into the realm of time crystals was just beginning, and the possibilities seemed limitless. After Wilczek's proposal, physicists quickly pointed out a problem: thermal equilibrium. In equilibrium, systems settle into maximum entropy. Motion ceases except for random jiggling. A ground state should be perfectly static. A formal proof showed that no system in equilibrium could break time translation symmetry. For a while, time crystals seemed impossible, just a beautiful idea. But physicists realized the no-go theorems only applied to equilibrium. What about systems driven by an external force, like a laser pulse? This led to the concept of a floquet, or discrete time crystal, a system nudged with a regular beat, responding with its own rhythm. Instead of mimicking the drive, the system could lock into a new, longer period, a true signature of a time crystal. The focus shifted to finding stable, periodic responses in driven, non-equilibrium systems. Building a time crystal in reality was a huge challenge. Quantum states are fragile and easily destroyed by their environment. Scientists needed a platform that was both controllable and isolated, a quantum computer. In 2021, Google and collaborators used their Sycamore quantum processor to create a time crystal. They programmed the chip's qubits to act as interacting quantum particles, then applied a periodic drive, a repeating sequence of pulses. The qubits didn't just follow the rhythm, they oscillated at half the frequency, creating a new, stable rhythm. This was the smoking gun. The system had broken the symmetry of the drive and chosen its own beat. Even when errors were introduced, the time crystal's rhythm persisted. For the first time, a crystal's pattern was etched not in space but in time. Humanity had created a new phase of matter. To understand time crystals, we need to shift our perspective a little. Think of a regular crystal, a salt grain for example, something familiar and easily visualized. It's made up of atoms arranged in a repeating pattern in space. This spatial order is what defines a traditional crystal. Now let's stretch our imagination and envision a material with a pattern, not just in space but also in time. Imagine its atoms or qubits oscillate, moving back and forth in a predictable manner. This oscillation occurs in a synchronized rhythm that persists indefinitely, a perpetual dance at the quantum level. A time crystal doesn't have a static lattice like a regular crystal. Instead, its components form a repeating pattern in time, a cyclical behavior that defines its structure. It's like synchronized swimmers, each performing their part in unison, moving together in a periodic dance, a beautifully coordinated routine that repeats over and over. This happens spontaneously, without a choreographer dictating their every move. It's a self-organized phenomenon. Even in its lowest energy state, where you'd expect all motion to cease, this motion continues. It defies our conventional understanding of equilibrium. It's a collective pulse, a synchronized movement chosen as the most stable configuration for the system. Unlike a pendulum, which needs an initial push to start swinging and eventually stops due to friction, A time crystal's motion is intrinsic to its ground state. It's inherent to its very nature. In labs, discrete time crystals are periodically pumped with energy to observe and control their behavior, but their response is a new, stable rhythm, a frequency that's different from the driving force. So a time crystal isn't just any oscillating system, it's something far more profound. It's a new stable phase of matter, a fundamentally different way for matter to exist. Just as water freezing into ice is a phase transition, a change in the state of matter, so is the formation of a time crystal, a transformation into a new form of matter, a transition into temporal order, where time itself becomes a structuring element. This order is protected by collective interactions, by the way the particles interact and coordinate with each other, making it robust and resilient against external disturbances. Time crystals are not fleeting effects or transient phenomena. They are not here today and gone tomorrow. They represent a new way for matter to organize itself, not just in space, but across the dimension of time. They represent a phase transition, not in the familiar three dimensions of space, but in the dimension of time, opening up entirely new possibilities for material science. This is what makes time crystals truly unique and a fascinating area of ongoing research. Symmetry is central to physics. Laws that are the same everywhere in space or time lead to conservation laws. For example, spatial symmetry gives us conservation of momentum, time symmetry gives us conservation of energy. A regular crystal breaks spatial symmetry by choosing a repeating pattern in space. A time crystal does the same for time. It breaks time translation symmetry. In the lab, time crystals are driven by a periodic force, but respond with a different longer period. By choosing its own rhythm, the time crystal breaks the symmetry of the drive. The system only returns to its original state after multiple cycles. This is a profound break matter organizing itself into a new temporal beat. It's as if a clock ticks every 2 seconds, even though the gears turn once per second. Symmetry breaking, which explains the structure of matter, now applies to time itself. Time crystals show that the laws of physics can be bent in the dimension of time. This discovery expands our understanding of symmetry and order in the universe. Time crystals are more than a curiosity. They could revolutionize quantum technology. Quantum computers struggle with errors from environmental noise. Time crystals' inherent stability could make quantum systems more robust and error-resistant. Their collective rhythm can help correct errors, making them ideal for quantum memory. Time crystals could also serve as ultra-precise sensors and clocks, with oscillations protected from noise. Imagine networks of time crystal sensors mapping gravitational fields or detecting faint cosmic signals. The creation of time crystals is just the start. Scientists may engineer other exotic phases of matter using periodic drives. Time crystals are the first of many designer quantum materials, created by programming matter with rhythm. The discovery of time crystals has changed our understanding of matter. We've added a new phase, one defined by temporal rhythm, not spatial arrangement. Time crystals force us to rethink time itself. At the quantum level, matter can impose its own ticking beat. This could be just the beginning. What other temporal phases might exist? By breaking time symmetry, we're probing the bedrock of physical law in new ways. The questions raised are profound, touching on the nature of order, equilibrium, and existence. Are time crystals a niche phenomenon, or the first glimpse of a deeper principle in the universe? For now, they stand as a beautiful, enigmatic monument to the endless frontier of knowledge. If you enjoyed this video, don't forget to subscribe, leave a comment, and ring the bell for more fascinating science stories.